suggested areas for research which come out of my experience. The reason I've reduced the emphasis on the scoping studies a bit is basically that there aren't any pictures. So there are reports freely available on the web. If people are interested in the detail on that, then it's possible just to read the things instead of having me effectively read them out and probably get it wrong or something. Okay, so where do I come to this from? So I'm not a statistician, though I tend to be a committed advocate of statistical thinking, and I work a lot with people who are very good statisticians. So my original background is in theoretical physics, and where I came to thinking about uncertainty quantification in large models is really that. Because when I was sort of, if you like, growing up in theoretical physics, the thing you learn at your mother's knee is that if you have a model with a large number of parameters, no one will believe anything you say, because they'll just say, well, with that many parameters, you could just make the outputs of the model do anything. And in that community, a large number of parameters would typically mean about 3. So you kind of then go to sort of the world of energy systems modelling that I've spent most of my last 12 years in, where 10 to the 4, 10 to the 5 would not be all that big, also a lot of the examples I'm going to give are somewhat to do with energy. I think that I don't make any apology for that. I think one of the key points here is, which I think has come out in some of the talks already, is that when you take a step back and think about the deeper issues in modelling methodology for complex systems, the questions we're asking are not landscape specific, they're not energy specific, they're not infrastructure specific, they're deeper questions than that. Okay, so first I'll give a few examples arising from energy experience. So this is just an example of how much directly relevant data do we have. So this comes from work on electricity security of supply. It's just a scatter plot of daily peak demand against how much wind generation is available. So you have all these dots. You have, if you don't just plot daily peak demand, you'd have thousands upon thousands of dots. But it's actually only these ones that actually matter, and these probably come from about 4 weather systems in 3 historic winters. So you think you've got all these numbers, all this big pile of numbers. Actually, you don't really. And again, this is something that needs to be confronted head on. You also have further issues when you're looking at pretty much anything on capital planning or policy time scales, that you often don't have directly relevant data at all for many purposes because the future has not yet happened. I don't need to go through this much. This is a slide that because Danny's already said much of this. This is a slide that I borrowed wholesale from Michael Goldstein. One thing we'll just emphasise again is that if you have a high-dimensional model where evaluations take a long time, you can only cover the input space sparsely with evaluations, and in order to tie things together logically, you need something like an emulator. And this thing saying example of objective function, this isn't actually supposed to make sense in isolation. It's a cue for me to give a particular example which works much better with chalk than on slides. So this is actually the second consecutive workshop I've spoken at the Newton Institute where I think I've been the only person to use chalk, which is a bit surprising because I'm one of the less dedicated Blackboard people. So if you think about optimization, conventionally that's what you think of optimization as. You have some sort of sharp line and you're looking for the bottom of it. But what you have when you do a full uncertainty treatment is that your objective function looks something like that, but you're not quite sure what it looks like. Or at least if you think of what the analogous objective in the real world looks like, you're not quite sure what it looks like. And then instead of just looking for this sharp point, what you have, and will I get this right? Yeah, you find that you can rule out everything outside these outside this band, but you don't have the ability to say that there is, even in model world, there is the objective, the optimum. And then of course you can maybe do a better emulator and refine this, and it's a little bit like the NROI, the points not ruled out yet in history matching that Danny referred to. The situation you get is that if you take this picture, there are lots of we know lots of efficient ways of doing the computation for optimization, but often we don't have a framework for adding on a full uncertainty specification. In this picture, it's a natural. You would have a natural way of adding uncertainty specification, but not, to the best of my knowledge, not a great deal is known about how to do the computation, and I would be delighted if I'm wrong about that. I also can't even use the punchline on this slide because Danny's already got there. This is an example from energy systems that illustrates a case where it's just intuitively obvious that you're not going to get very far by a detailed bottom-up system model. So it doesn't matter what the units mean, but the size of the Great Britain electricity system is, well, peak demand is just over 50 gigawatts, so yeah, it's of size 50. The European system is about 500 gigawatts, so it's 10 times larger, and the link between them is currently of size 3 gigawatts. So, so what you're interested in thinking of the contribution of Europe to security of supply in Britain is about 3 gigawatts on the margin of a 500 gigawatt system, and it is totally implausible that you could ever pin down through bottom-up modelling what the European system is like to the degree that you would need in order to explore this 3 gigawatts on the margin. You also, of course, have the point that any kind of bottom-up model of this lot would be complex and high-dimensional. And again, this is where maybe some sort of different modelling approach, maybe something a little bit more along the lines of the thinking top-down about system structure as relating to Martine's presentation yesterday would be appropriate. Of course, in this particular example, just to add to the fun, you have a multivariate time series with focus on the extremes. So, even before you get to doing any system modelling, you're knocking on the boundaries of statistical methodology as presently known. So what I've answered speaking on the second day is that I get to put up a diagram that's already been presented, and I was wondering whether instead of the Harrisonogram we could call it the Niceogram. But I think almost the kind of point of thinking about the so-called Herendogram is the fact that if I put it up like this, even if this was all that was on the slide, you still wouldn't be able to read it. And you also have mapped onto this the fact you're looking at evolution over time. You're possibly, for some purposes, looking at a time horizon of decades for taking policy decisions. This is a situation where you end up with, well, if you try some sort of bottom-up system modelling again, you will run into the situation where as the model becomes bigger and more complex, you need more runs because you've got a higher dimensional uncertain space, but you can actually do fewer because each run takes longer. And so you get to the situation where you kind of add more detail hoping to learn more, but it actually becomes harder or maybe impossible to work out what you are learning. And I think this topic of decision support in very complex situations where the real world is just, and the degree of sort of futurology uncertainty is far more complex than any model, is a really vital issue, but it's one that's rarely addressed head on. And I hope that's something I'd very much like to talk about. And this is a very general methodology issue. It's not just about energy and environmental modelling. This is a point that came out of discussions with someone from the operational research profession at Business Energy and Industrial Strategy, and they use for a lot of purposes the UK Times model. It doesn't really matter what it is, apart from the fact that it's basically a big linear program. And they're looking at understanding impacts of policy over, say, a 50-year horizon. So in principle, this is a white box model. So you have all the data. There's actually only about, in the LP specification in a modelling language, there are only actually about 15 classes of constraints. So the actual underlying mathematical model structure is something where a human being can look at it and actually really have a total overview of the model structure. But what you actually end up with when you bring together the data and the linear program is some enormous non-linear mapping from inputs to outputs with greater than 10 to the 5 variables and constraints. In fact, I think 10 years ago when I was first thinking about this, it was 10 to the 5. It's probably gone up to about 10 to the 6 now. And so what you end up with here is that you have what in principle is a white box model, but in terms of explainability, it exhibits many of the features of a black box model that we think about in machine learning. And the question posed by the person from Bayes was, sorry, that's Bayes, B-E-I-S, not Bayes, B-A-Y-E-S, because sooner or later we'll probably end up with a project using Bayesian statistics, collaborating with Bayes, cited in the Bayes Centre at Edinburgh. And the question posed was how to understand what is driving outputs. And this is actually a question where there's a serious point here before we get anywhere near thinking about the real world. This is simply quite a challenging question in model world. And I was kind of thinking of a term for this, and I came up with do we call it a chessboard model, or do we call it a yin-yang model? I don't know. I'll get on to, so I'll talk a little bit about the various scoping activities I've been involved with. So really serious interest in thinking about these general issues in modelling for public policy started with a workshop under the auspices of Supergen HubNet Energy Networks coordinating projects about 2 years ago. This was hosted by Ofgem, the regulator. And two things to say from that. We were interested and quite pleased that not only because this was directed by the questions we were asking people, what we didn't get was a kind of sort of menu of specific applied modelling tasks that people were interested in. The dominant themes were things that often come up, but it was interesting that it was these general questions that were really coming up, was highlighting needs for treatment of uncertainty in modelling, the importance of communicating evidence, and also thinking more broadly, ranging from how decision processes work to curation of models, of how modelling sits within overall policy processes. The other thing that came out of it was that we first learned about the Aqua Book, which is a manual produced by HM Treasury on what constitutes quality analysis for government. And this is a superb quality document. I mean, even Michael Goldstein said it was a superb quality document, and if Michael doesn't like something, you quite quickly know. But it says some very radical things about how government, about what you should aim for in treatment of uncertainty in modelling. And this actually led quite directly to projects at the Alan Turing Institute called Managing Uncertainty in Government Modelling, looking at how we can help people meet the requirements of the Aqua Book in practice. The second half of last year, I and others, including Henry Wynne, ran a network for Centre for Digital Built Britain on planning complex infrastructure under uncertainty. And again, coming out of this was what you might call all of the usual stuff. And I don't mean this that it's unimportant. It's just that it's kind of things that are more commonly thought about as needs. But other kind of less. Slightly less obvious things. Determining a lot of areas before any full-scale projects could work. There's simply not a lot of collation of knowledge on what people were currently doing, or what the detail of what the real-world situations look like. So there was clearly a need for some preliminary detailed scoping work or information gathering. Specifically in the area of infrastructure projects, there's a need for a more nuanced understanding of success and failure. So, budgets and for a £10 billion projects, budgets and time to completion are not deterministic when you start digging, and often it's treated in the political or media debate as if they are. Communication is a two-way process. Not only do we need good communication from analysts to decision makers, we also need to make sure the analysts understand properly the circumstances under which they're making recommendations. Appropriate level of resources for strategic planning. Quite often, I mean, £1 billion is not a particularly large project in infrastructure, but often it turns out there was pretty universal agreement that it often turns out that the small amount of resource put into analysis for the early decisions on what do we build, how big and so on, are not commensurate with these enormous capital budgets. And there was value of wider availability of data. And also, I'll come back a little bit to good design of funding structures to make sure you can get the right people together. And I don't really need to talk about the Isaac Newton Institute for Mathematical Sciences as a place where we have scoping studies in this kind of area. Just recapping a few sort of issues we might think about in the programmes. This issue of thinking about decision making against very complex backgrounds. I think it's very important to remember that in many areas, we'll have a common methodology core where there could be different application areas, and this might, with anything NERC is doing, it might create opportunities for a project in collaboration with, say, the energy programme, where you have a methodology core and there are different application work packages. We have these issues of explainability of models with my sort of black and white thing. There's all of the issues of how decision and analysis sits within the overall decision process, because it's human beings who usually aren't analysts who are actually taking decisions. And there's my thing about what if you're not quite sure what the objective function looks like. One nice thing about speaking near the end of the workshop is that it's possible to reflect on a few things that have already been said. So one point with this thinking, it was something I often say anyway, but it kind of follows on from remarks Gavin Stewart made about the about presently things having to fit within the framework of the Treasury Green Book. And I always think there are different timelines on which we need to think about when methods might come to use out in the field broadly. And obviously we want to help people immediately in the next year. I mean, in academic terms, this is probably consultancy. We also want to be doing things to be in the best place to do analysis in 3 to 4 years. You can't achieve that by consecutive incremental annual cycles, but this would probably be within current general structures. But also we need to be thinking, well, what might analysis look like in 5 to 10 years if we think we maybe don't need to stick in current structures. And I hope we'll be able to think about all of these in the current programme, and in particular, I don't think we're really doing our jobs as academics unless we're thinking about the 5 to 10 year stuff. Again, I echo Henry Wynn's comments there. So also an important issue is are we always learning more if we're kind of adding more detail in one of these situations where the real world is exceptionally complex, or is that the right general approach? I'll just conclude with a few of these reflections on bringing together a wider range of disciplines. So as you gather, I may have used this slide previously, but I thought this was actually quite a good way of illustrating that the issues are very, very similar. I think one challenge you end up with, obviously, this discipline is this application area is something of a showing the way here by having this very explicitly interdisciplinary meeting to try and get the right people doing the doing the work, but in particular there's a general challenge that the best people to do certain methodology things might not have a track record in the relevant application area. Is this kind of work rewarded? I mean, historically mathematical sciences has been a bit notorious for not doing. This is changing somewhat. Challenge of knowledge transfer when the kind of the statistical or analytical methods required are really not familiar in the, say, the government analyst community. That's largely what our Turing project is about, and particularly the need to have the system or physical modelers working together with uncertainty people or social sciences or whoever else from an early stage, which is quite rarely done. Quite rarely get everyone together at the very start of designing a study, and that's really how it should be done. Finally, I think the picture is optimistic if we can make these links, but we need to get cracking on it. I think that's why I'm so pleased that this workshop and programme exists at the Newton. And finally, I'll just leave with this thought of my kind of summary of the basic requirements for an applied study. And it's interesting to think how many studies one observes satisfy number 2 or even number 1. Anyway, thank you.
Thank you. Thanks, Chris.